For this next session, we'll hear from Joanna Young, who is the product leader for Google Confidential VMs and Confidential GPUs. Joanna has been working at Google for over 4 years in cloud security, where she has launched and driven customer adoption of multiple confidential computing products. Let's jump in.
Yeah, thank you everyone for choosing today's session, Confidential AI Use Cases on Google Cloud. Jump over to the first slide, which is the table of contents. It's pretty short. We will start off with kind of the problem space of cloud security, move into how that impacts kind of AI ML workloads, talk about some solutions we have for these AI and ML workloads, and a unique use case that what Google Cloud calls confidential space, but is actually untrusted multi-party compute. So starting off with the problem space, I think data protection today, for many people still, their data is on-prem. They know where it is, they control it, and they're responsible for protecting it. Now, a lot of people have moved a lot of their data into the clouds. So now they do kind of hybrid. Maybe they have some on-prem, maybe they have some data on the cloud. And now that model of data protection and security changes, because now that protection is now shared responsibility between not only the data owner, but the cloud provider where the data sits. So that naturally brings up a lot of concerns on these people who are trying to move to cloud. Like, they used to be the ones that needed to protect their data, but now they need to ensure that their data is also protected in the cloud. So protecting sensitive data, whether that's the code or the data itself, that's always a key concern. Another one is staying compliant with data protection regulations, especially with our customers in Europe. You can easily see all these new data privacy, data laws and acts coming in to ensure end users and customers' data are protected. The third one we commonly run across is kind of that untrusted multi-party compute. So maybe it's a customer who wants to collaborate with other customers, but each of them don't want to share and reveal their own data sets, but they just want to share the final results. And lastly, these cloud customers that Google Cloud has, they also have users and clients. And so a lot of times they are like, I need to be able to prove to my end customer that I don't have access to that end customer's data. So it's almost like a nested situation going on for that last one. Okay, but you might be like, oh, this was an AI presentation. This just seems like random generic data protection. Well, a lot of these translate to AI concerns because AI is built on massive quantities of data, sensitive training data, sensitive prompts that you're typing into, ChatGPT. So what you can see is that easily that first one of sensitive data, maybe now this customer wants to protect their AI model and make sure that their models are not tampered with. Staying compliant, that still remains a key concern when they're handling sensitive data sets and models. So, even when you're creating these models or delivering these models, like there's privacy and copyright laws that they need to stay in compliance with. The third one is also very applicable. Once someone maybe creates a model, they need to share that model on an exchange, but they don't want to lose control of their model. They don't want to give away their model for free. They want to be able to allow customers to use it, but not have customers, monetize that. And lastly, protecting end user data. Well, that's very applicable to prompts and inputs that maybe a customer uses to generate, a response from a chatbot, but they had to include maybe their own sensitive data. And the provider of the chatbot may not be able to want to be able to access the user provided input, kind of that end user situation. So all of this is to say that, data protection, is still key and top of mind for AI and ML workloads. Okay, so what do we recommend? So as a security specialist, we recommend a very common principle called defense in depth. So a common way to protect data is encryption. I think people are very used to encryption at rest. If you were to dump a hard drive, it would be encrypted bits that potentially come out because you've encrypted your storage. People are really used to HTTPS, right, rather than TP, right? Because they encrypted their data in transit. Okay, but what about that third leg? How do we protect sensitive data that's in use? How do we protect the model, the AI model, when it's running? And I'm going to introduce you to a concept called confidential computing. I hope you've heard of it, but maybe not. If you haven't, confidential computing is the protection of data in use through hardware-based technology, and it creates a trusted execution environment. So we'll talk about that more on the next slide. But so confidential computing, it helps keep data and code protected while it's being processed. So really providing that end-to-end encryption that I mentioned before. Now you have data at rest encrypted, data in use encrypted, and data in transit encrypted. You can have all three, that trifecta. So there's two key components I want to talk about for confidential computing. So one is the trusted execution environment. And that really answers the question, that concern of how do I protect my data and code, while it's being processed. So let's say you have confidential data, you have your trusted software, your application that's running. You want to make sure that unauthorized parties, can't access your data. This is your proprietary stuff. It doesn't belong to anybody else, and no one else should access it. That includes the cloud service provider itself. Yeah, you're going to host it on Google Cloud. That doesn't mean you want Google Cloud to be involved in seeing your data. And so what confidential computing provides is that trusted execution environment to prevent unauthorized parties, including Google. So the host infrastructure and the hypervisors are considered untrusted in the confidential computing model. So I think that's really key because, I just said that, in the prior slide, that it's shared responsibility when you put things into the cloud. But confidential computing kind of shows a paradigm where, yeah, you put it in the cloud, but that doesn't mean I should trust the cloud provider in its entirety. So on the right-hand side, I think it's a very critical component of confidential computing called attestation. So, okay, yeah, fine, you've enabled in confidential computing, but how do you prove that it's actually enabled? Well, there's a concept called attestation where you can get hardware-based cryptographic evidence that your workload, whether it's a VM or a container, is indeed running confidentially. It's running with that data encryption in use because, like I said before, confidential computing is hardware-based. So because it's hardware-based, you can have the hardware produce cryptographic evidence that you can you can generate an attestation report that you then verify with perhaps the hardware vendors to ensure it's a valid signature on the attestation report. So what happens is when you validate this TEE state, this trusted execution state, you can ensure that your workload is running on genuine CPU hardware, that you have the patches that need to be there, you're running on the latest software, and that it's running on authenticated firmware. So it's not only about protecting your data, but it's also about validating and verifying. And that validation and validation and verification really helps build that trust, especially when you're trying to prove to whichever user you want, whether you want to be trying to protect your data from the cloud service provider, whether you're trying to protect your cloud service, your data from other users. It's really the combination of these two that make confidential computing so powerful. So, okay, let's bring it back to AI. Okay, so then what's confidential AI? Well, that's the topic of this presentation. Well, it's applying confidential computing to AI and ML workloads, right? So like we said, the whole process of creating AI ML workloads, like there's so many pieces that involve data, proprietary IP, all of this needs an additional defense in depth layer called confidential computing. So what I have here on this slide is, in the beginning, when you're gathering that data for the model to be trained on, like there's a lot of data ingestion, there's a lot of pre-processing that's involved. I've had customers come to me saying, hey, I want to protect my training data. My data labels is what's important, what's really proprietary to my company. That's what I want to make sure that stays protected from unauthorized access. On the second stage, model training. So when you're doing a lot of this compute, you're computing on very sensitive data. And so you want to make sure that during that training, you're also protected. Number 3, for model fine tuning. Okay, so now you've got a model and now you're doing some fine tuning. You're putting some extra sensitive data in there. You want to make sure the models and the model weights are not tampered with. So that one's definitely come up in our customer meetings as well. Number 4, model deployment. This is the key one. So you created your model. Now what? Now you need to distribute it and have people use it, but you don't want to lose control because that model was expensive to build and you own it. And, you know, maybe you want to make sure that people can access it without, you know, stealing it or, you know, tampering with it. And then lastly, inferencing, you know, protecting maybe whether you're protecting your end users' prompts or whether you're protecting your own internal employees' prompts, and you want to make sure they're protected as well. I want to call out, you know, all of this is all still subject to data privacy and compliance regulations. So, you know, throughout this whole AI development lifecycle, you don't want to break any copyright or privacy laws. Very key. So what's the solution here? So there's one that I want to start off with. Of course, there's many solutions, but confidential VM is kind of where we start with the infrastructure. So we added confidential. So at Google Cloud, what we've done is we've taken confidential computing. We agree with the principles of strengthening data protection, and we've added it to our infrastructure kind of flagship product when it comes to VMs, our Google Compute Engine product line, which helps you create VMs. And so you have a Google Compute Engine VM, and you have confidential computing added to it, and we call that confidential VM. So what it does is that data encryption while in use. So as we talked about, it uses a specialized hardware to create a trusted execution environment. So now your data is encrypted. So the memory is encrypted and decrypted only on the CPU chip. Google does not have access to the keys that are encrypting and decrypting the memory. These VMs are highly scalable. And there's minimal performance impact with the encryption and decryption, especially since it's hardware-based. There's an encryption engine built right onto the chip. And it's also available with Ubuntu LTS and Ubuntu Pro. So the other cool thing is really no code changes needed. So, you know, honestly, if you have a regular VM, you should be able to run it in a confidential VM. And I think that's a really key piece about Google Cloud adopting confidential computing, is making it very usable for the end user. So hopefully you can just, you know, try migrating one of your VMs over to a confidential VM and see if, you know, how performant it is, how much more secure it is, and how it really puts kind of that trust boundary, kind of the need to trust, you know, other softwares outside of your own code, much more diminished. So we'll see that in kind of the next slide. So one of the technologies of confidential computing is called Intel TDX. And so remember I said confidential computing is hardware-based. Well, Intel came out with their confidential computing technology called Intel TDX, Intel Trust Domain Extensions, where each VM becomes its own trust domain. Like, that is the domain I trust. There's multiple trust domains. Let's say on a physical host, each of these trust domains are kind of isolated, cryptographically isolated from each other. So, you know, I've thrown a lot of acronyms at you: Intel TDX, confidential computing, confidential VMs. Okay, one more, but not the last. Intel AMX, right? So, like I just said, that the confidential VMs run on a confidential computing technology called Intel TDX. And I specifically said that they, on Google Cloud, are on the C3 machine series. Now, these C3 machine series run on that 4th generation Intel processors. And those 4th generation Intel processors are also equipped with a built-in CPU accelerator. And this is where that AI ML story comes and kicks back in. And it's like, now you can have a confidential VM that has CPU-based acceleration built in, default, already on. And this Intel AMX Advanced Matrix Extensions has been built for deep learning training and inference on the CPU. So I think Intel mentioned that, you know, their previous generation of this technology it was really commonly used for inference, but for this next generation of their CPU accelerator, that they really wanted to focus on training use cases. Obviously it won't be a giant foundational model training where you're going to need thousands of GPUs, but for a single GPU, you should be able to do some small training, and they have some metrics also published. So it's, again, on the left-hand side, like I mentioned, they're on by default for the confidential VMs that are on the C3 machine series. In the middle, it is improved performance from their previous generation. Great for matrix multiplications. Obviously, it's matrix extensions. And lastly, that key piece is easy to use. They have, Intel's provided integrations with PyTorch and TensorFlow, and those AMX instructions can definitely be leveraged. Okay, so now I'm going to go into, what Google has done. So Google saw this technology, saw Intel AMX, and was like, all right, let's run some experiments. Let's validate the training and inference performance. So we have 3 VMs that we compared. The first one is that 3rd generation Intel Xeon processor called Ice Lake, that top line. And those Intel Xeon processors did not have confidential computing, does not have Intel TDX, and does not have Intel AMX, that CPU acceleration. Okay, so that's the first one. That's called the N2 VM. That's available also on Google Cloud. And then we have the second line, which is the general purpose C3 VM that I talked about. And those are running on the 4th gen Intel Xeon processor that's nicknamed Sapphire Rapids. And so that one we decided to, we didn't enable TDX on that one. You technically could, but we didn't turn it on. It's optional. And then, of course, it has Intel AMX, that CPU built acceleration, on by default. Okay, so that's the second VM. And then the third one is now the C3 plus TDX. So now you've added confidential computing to that C3 VM. Now you've got a confidential VM, again, running on the 4th generation. So now you can see not only comparing between generations, 3rd gen to 4th gen, but you're also comparing confidential on and confidential off. So that 3rd VM, you've got confidential on, and you've also got that CPU acceleration on. So we ran some training experiments. So the training experiment we did is we fine-tuned Roberta. It's a large language model that provides improvement over BERT, which is another large language model. And it's commonly used in natural language processing applications. Okay, and so we evaluated the large language model on question answering applications with the Stanford question answering dataset, abbreviated SQUAD. And so the team used Hugging Face Trainer and PyTorch frameworks to evaluate and leveraged its integration with the Intel AMX extension for PyTorch, Intel extension for PyTorch, so IPEX. And so what we did was compare training time between the 3 VMs I talked about, right? So on the left-hand side, you have that VM that doesn't have Intel TDX on, that doesn't have Intel AMX. And you can see how long training time took. And so lower is better for training time. It's more efficient if you spend less time training. That middle section is that C3 VM with no Intel TDX enabled. However, it does have that Intel AMX. And you can already see how drastically the training time has dropped in minutes, right? And then on the right-hand side, you have the 3rd VM, which has the Intel AMX feature on, and it also has the Intel TDX, right? So not only is it super performant for AI/ML workloads, but now is also securely processing data. So that's the C3 plus TDX. And you can see between C3 and C3 TDX that the 2 VMs are pretty similar in training time. And so what we found is compared to the N2 VM, that first kind of that 3rd gen Intel processor, the C3 VM provided a 4.54 times speed up on training time. And then the C3 plus TDX VM provided a 4.14x speed up time for training. And so you do see that there is some performance impact when you enable TDX, but still very good performance for training. It's not even inference, we're talking training here. So, and this is just with a CPU acceleration. Okay. So Intel AMX, we also ran some AI ML inference experiments. And so we did a text generation task on two LLMs, the Llama 7B and the Llama 13B. And so again, we're comparing the same kind of three VMs, the N2, the C3, and the C3 plus the TDX. And what we evaluated these three VMs on is time per output token, so TPOT. And you can already see kind of from the colors, the light blue is the N2, the dark blue is the C3, so that's the C3 with only the Intel AMX, but doesn't have the TDX, and then you can see the AMX plus TDX in orange. And what we found is compared to the N2 VM, that the next generation VMs with the Intel AMX provided kind of a speed up of 3x for TPOT and kind of 7x for throughput. And just to call out on the inference experiments that they were using DeepSpeed, which is an optimization library, and it was averaged. These results are averaged over 50 runs. Okay, so back to the presentation of use cases, right? So we've talked about Intel TDX, we've talked about AMX. So what? So what do we do with this? We secure AI workloads, right? So one thing we've seen is recommender engines, right? Recommender systems use a lot of sensitive end user data, and what you can do with that is have machine learning deliver customized end user experiences. So deep learning recommender engines can easily be protected and run performantly with Intel TDX plus AMX, right? So you can protect the real-time user behavior, signals, data, and context during deep learning. Second one, natural language processors. We just saw that with Roberta. You have a chatbot. It's performing maybe sensitive sentiment analysis on user data, and that needs to be protected, maybe doing machine translation. And with Intel TDX and AMX, you can secure the training data and you can secure the queries during inferencing. So now you can start to see kind of a pattern of how these go. Lastly, we've seen this adopted in retail. So in retail e-commerce, let's say you're trying to minimize transaction times, do a lot of forecasting. Forecasting has a lot of revenue numbers that are sensitive. And you want to protect that. So you can use Intel TDX and AMX to ensure that end user customer data or your own revenue data is protected from unauthorized access throughout, training, fine tuning, inferencing. All of these are applicable. And again, this is all just with CPU-based acceleration. So we need to talk about something else, something bigger, maybe more performant. GPUs. So NVIDIA has a GPU called the H100 Tensor Core GPUs. And these are fantastic GPUs as it's NVIDIA's first confidentially computing capable GPUs. So we just talked about all these CPUs, making sure they're confidential computing enabled and they're providing these trusted execution environment. Now what NVIDIA has done is they've taken these GPUs and strengthened them and hardened them, and now they're part of the trust environment. Prior you were just kind of on that CPU doing CPU-based acceleration. Now you can add a GPU to your confidential workload and still ensure that trust boundary is as secure as before, right? So now you can validate now that GPU is brought into that blue boundary. And so these are NVIDIA H100 Tensor Core GPUs, and they provide strong hardware-based security while remaining performance. Really, performance is still key. We're still talking about compute at the end of the day. Middle section, only unauthorized users can place data and code for execution within the trusted execution environment. So now that CPU and GPU environment combined. And you have that key piece of device attestation, proving that your data workload is truly running confidentially, not only on a confidential computing enabled GPU, but also on the CPU side. This mitigates threat from, operator access, unauthorized access, and even the hypervisor. Very similar story to the CPU, as again, it's extending that confidential computing protection over to the GPU. And most importantly, no code changes required. We're trying to really, I think everyone in the industry is trying to push this. Should be easy and should be this similar experience as the non-confidential version. So Google Cloud plans to provide the confidential GPUs, and so you can sign up here on this interest form, and if you sign up on the interest form, we'll let you know the next steps and updates on this product line. Okay, confidential GPU. What does it do? What exactly is happening here? What do you mean by you brought it into the trust boundary? So the transfers, the data transfers between the CPU and GPU are now encrypted. So the data transfers are encrypted and decrypted at the Peripheral Component Interconnect Express, also known as PCIe. And so you can see on the left-hand side, typically the host OS and the hypervisor technically has full access to the GPU in the cloud, and your VM would communicate with the GPU that you requested, and the transfers between the VM and the GPU are unencrypted. Now, with confidential computing mode on, you've now created a trusted execution environment around the VM and around the CPU. I'm sorry, around the VM and around the GPU, and the host OS and the hypervisor do not have read or write access. So the data is encrypted between the CPU and GPU, and you've locked that host OS and hypervisor out. So really shrinking that trust boundary, that one slide where now you've got the host OS and hypervisor outside of the trust boundary. It should not have access to your confidential data. And this is so exciting because there's so much confidential data that needs to be leveraged when it comes to AI ML workloads, and now you can do it securely during processing. Okay, back to kind of the key point. So what? So what? Now you've got a secure GPU. Well, you can use it to protect AI ML workloads, right? So, you want to protect AI intellectual property. I think this is really key. We see it a lot, maybe in financial services, where they have maybe a model that needs to be fine-tuned, and that is their sensitive proprietary financial data. The second one, for training and inference, during those times, you have massive amounts of regulated data. Maybe PII is in there, maybe it's patient hospital data, so very applicable to healthcare. Again, these are not mutually exclusive or anything. Sure, a lot of industries can benefit from all these categories. But really the coolest part is that third use case that we briefly touched upon in the beginning, called secure multi-party collaboration. And this is really when you have multiple organizations that want to work together. They want to train and evaluate AI models while ensuring their data and their AI models are protected from unauthorized access, external threats. And maybe it's not just the models, maybe it's the data that they're doing data sharing, and they want to protect their data even though they're in a collaborative space. Maybe this is very applicable to a lot of advertisers, advertising companies, where they have a lot of user data, but they're not allowed to share it with others, but they still need to have customer targeting, and so they need to collaborate securely without revealing their own individual data sets. And so that brings me to confidential space. So confidential space is a secure, flexible infrastructure where only the trusted workloads can access the data, and it also prevents data access by other users. So that's a lot to digest. So the first one is one, you can put data into a trusted environment, and that's the only data or application that's running or that's allowed in that environment. So one, you can verify what is put into this environment is exactly what it says it is. And how do we know that? That attestation piece. And then what that does is also that second piece, right? So now you've proven what is running is indeed what's running, and then also preventing data access from other users because you created a TEE environment. So confidential space is a Google product, and it's built on confidential computing. It helps customers collaborate with external parties, maybe other customers, whether on Google Cloud or other clouds. And it helps those customers maintain confidentiality but still maintain full control over their own data, right? So, and then you can also perform joint machine learning That is very key because, again, we're talking about confidential GPUs, adding those kind of high-end computations to confidential space. And lastly, you retain full control. Confidential space releases data only to the authorized access, protects it from the operators, including the cloud service provider. Again, that's confidential computing at its best in a real-world application. All right, so let's jump into a demo. So the first one is, I'm going to explain demo before we jump into the video. So the LLM plus RAG in TE kind of demo. So what we have here is two trusted execution environments. Okay, so let's say you have a large language model provider. They're in their cloud and they have a LLM that they have finished, they've trained, they've ready to let people use it, but they don't want to lose control of their language model. So they want to make sure access is controlled and no unauthorized access. On the right-hand side, you have a customer who wants to use the large language model, but they also don't want to give the large language model provider all of their own proprietary data. It could be hospital records, could be financial data, could be retail customer purchases. Like that's their separate database. So for the retrieval augmented generation, that's RAG. So they put their stuff in a database. And so now you've got an environment where the generic LLM is running. You've got an environment where the vector database with the customer data is running, and they both need to be secure. And they both need to be running trusted and in a trusted execution environment in order to provide the end user, maybe the customer who's asking questions. And they were adding that the user wants to receive answers that are augmented with the vector database that that contains that customer's data. So for example, you could have maybe the large language model provider is party 1 and party 2 is that customer. So you can see how it's color coded. All right, and now we're going to jump into the video. So here, the first one is that left-hand side, that large language model provider, where it's running with confidential computing on. It has the Intel TDX. And then we also want to highlight the vector database, and it is not set up properly. That vector database is not trusted execution environment. You can see it's highlighted in red. And the question we ask is, what is Intel TDX? And unfortunately, because it's unable to attest that the RAG database model is indeed running confidential, there's no response. It can't attest, and so there's no docs. I can't answer the question in the chatbot. And now the chatbot is asked, hey, without the RAG data model, without the RAG database, a question: what is Intel TDX? And that one gives a kind of a misinformation answer. It's not taxonomy data center manager. You can see it's not using the context of the customer end user customer's data. So really kind of that hallucination is appearing. So now we go back and now we've turned on confidential computing on the confidential space VM. So it's a vector database is now attached and running with the large language model chatbot, and you ask its questions. Now the large language model has the context and the support of the RAG database, and it properly answers what confidential Intel TDX is, which is a hardware isolated architectural technology. And so you can see that it did not hallucinate this time because it's actually using the supplied documents that have now been attested to be running trusted. And that concludes the demo video. So we're at the key takeaways. We're near the end. The confidential computing is the protection of data in use through hardware-based trusted execution environments, right? That TEE is going to commonly seen. Now, confidential AI, you're applying confidential computing to protect AI ML workloads throughout its development lifecycle. And number 3, I think is really key, really focusing in on this use case that is just able to be unlocked with confidential computing. And that's the secure collaboration of AI ML data and models through a products like Confidential Space. And so don't take my word for it, try it out. So try confidential computing today. It's available. You can sign up for our GPU interest form on the left-hand side. On the right-hand, we've got our code labs for you to try out Confidential Space. Both of them are really exciting new things, to try and build your own use cases for confidential AI. And I want to thank you for attending today's session. I hope you enjoyed it, and take care.